going to talk about the special role of vacuum, as you see, in terms of the disorder that's very highly listed. You will understand much better at the end of the talk, actually. So this is the work which has been done in collaboration with all of these people. I've been carrying out this work when I was doing a sabbatical time at MIT together with Cerf and Jeff Shapiro. And Raul Garcia-Patron was a postdoc there at that time, and Carlos Maranete was a visiting PhD student at that time there. So in this talk will be a little more physics-oriented than the previous talks, but I hope that you will enjoy. So I will start by some very simple statements about a beam splitter, and I will question whether we really fully understand the physics of a beam splitter. Because you may all say that, yes, we understand the beam splitter very well. That's one of the simplest optical components. And indeed, if you think of a beam splitter in phase space, then in phase space, the beam splitter simply affects the transformation, which happens to be a simple orthogonal transformation, rotation, and everything is very simple. It is actually the perfect counterpart of the rotation affected by a beam splitter in classical electromagnetism. However, if you think of a beam splitter in state space and you start asking questions about the entropy, then as you will see now, actually some very simple questions are surprisingly still unresolved as by today. For instance, if you take a beam splitter as you see here, and you inject an input state here, an arbitrary input state psi, you only constrain the mean field, so you assume the mean field is 0, but it's not even necessary, but let's assume that. And you mix this pure input state here together with the thermal state at a beam splitter of transmittance T. So this can be seen as a Goshen channel actually, because you mix your input state together with the thermal state. The thermal state is a very simple Goshen state. And you look at the output state, it's a mixed state of course, and you try to minimize its entropy. So you ask the question, what is the least random input state? So what's the input state here which minimizes the output entropy? It is widely believed that such a state is the vacuum state. So it's very, it's also numerically confirmed that the input state here, which minimizes the output entropy, is a vacuum. Nevertheless, this isn't completely proven today. This isn't analytically proven today. Another related problem is the following. Let's now take for granted that the vacuum state is indeed the best state that we should inject in such a beam splitter. But let's now vary the environmental state. Let's vary the state here. So we assume that there is some entropy in the environment. So we fix the entropy of this state rho here. And we ask the question, what is the least randomizing channel? So what is the state of the environment here, which will again minimize the output entropy if I inject the vacuum? And again, it is widely believed that this is a thermal state with entropy, with the fixed entropy that I fixed here. So the thermal state is a Goshen state. Again, it is widely believed that this is the state which minimizes the output entropy, but this isn't proven. So in both these situations, you see that there is really a very special role played by Goshen states here, and this will be the topic of my talk. So in the rest of this talk, first of all, as you understood, yes.
Sorry, could you go back? You just have one output, but there are two ports out of the beam splitter. For
right.
Everything that comes out?
No. Here I'm only talking, I'm seeing the beam splitter. I mean, you could ask other questions, but here I'm looking at this beam splitter as a channel. Actually, the rest of this talk will basically be about channels. And so that's the input state, that's the output state. This is the environment input state, and I disregard the end. So I trace over this other part. So as I've said, most of this talk will be about channels, actually Gaussian bosonic channels. So first of all, I will state more precisely this conjecture which I've already introduced, which is called the Gaussian minimum entropy conjecture. And then I will talk about our contribution to this problem. I mean, first of all, we have linked this to the entanglement produced in the two-mode squeezer, and we have shown that there is a corresponding conjecture about the entanglement in such a squeezer, which we call it the Gaussian minimum entanglement conjecture. And then the core of our work is the link between this problem and majorization theory. So, I mean, first of all, we have stated still another, even stronger conjecture, but as a standard trick, we didn't know how to solve the conjecture, so we made another one. We call it the Gaussian majorization conjecture. I mean, again, this one is confirmed by the numerics, but we have been able to make, as an incomplete proof, of this majorization conjecture. And then I will conclude and try to convince you that this is really an interesting problem in physics. So how do we model a Goshen bosonic channel? So basically, just like any quantum channel, it is a CP, completely positive, trace-preserving linear map. So the difference with an ordinary channel is that it is Goshen. This means that if the input state is a Goshen state, then the output state is also a Goshen state. And the interest of dealing with Goshen states is that they can be mathematically described in a very compact way, because Goshen states and Goshen operations are very simple to describe within the so-called symplectic formalism. And in this particular case here, it so happens that the effect of this channel is completely encapsulated in two matrices, two real matrices, K and N. K basically tells us how do the first order moments behave in this channel, so how does the mean field transform in the channel. It's basically the rotation or the attenuation affected by the channel. And N is another matrix here which corresponds to the added terms. For instance, if we look at the fact that M is a completely positive map, this constraint translates into some constraints on the K and N matrices. And in the single mode case, these are the constraints. So this noise matrix should be a positive matrix. And we also have a condition on its determinant, which translates the uncertainty principle. This physically corresponds to the fact that many of these channels necessarily need to add some extra noise. I will explain why now. Actually, in this work we have been interested in a special class of Goshen channels, but actually the whole difficulty of the problem is already there. So we have been interested in phase-insensitive Goshen channels. These are Goshen channels in which the two quadratures of light, x and p, play the exact same role. So there is basically a phase invariance here. And in that case, not very surprisingly, the two matrices here can be considered as diagonal matrices. So the channel now only depends on two real numbers, tau and n. Tau is basically the transmission of the channel, and n is basically the added noise variance of the channel. So this means that every phase-insensitive Goshen channel can be seen as one point here in this figure. So the x-axis is the transmission, the y-axis is the added noise variance. For instance, this point here is the identity channel. The transmitter is 1 and there is no added noise. So here in green, you see all the purely lossy channels, which correspond to having a single beam splitter. So these correspond to situations where the transmission is lower than 1, and you see that there is some added noise variance here. This simply translates something we know very well, that the second input port of a beam splitter is fed with vacuum. In classical optics this doesn't play any role, but in quantum optics there are some vacuum fluctuations which are injected in this port. And this is the reason why we have some added noise here. This blue situation here corresponds to the ideal quantum amplifier. This is also a very well-known fact that if you try to amplify a quantum signal, the transformation necessarily undergoes some noise. This is the quantum noise, and this is this line here. So here, in blue, here you have the forbidden region. This is the region where there are no channels because of the uncertainty principle. Otherwise, each point here corresponds to one channel, and our problem will be to estimate the capacity of these channels. So let me just briefly remind you how do we treat the classical capacity of a quantum channel. This is of course a very old topic. This was introduced by Olivo, and then later on it was completely treated by Schumacher and Westmoreland. And this is based on the Olivo bound. So the basic object is the so-called Olivo bound, which depends on the encoding at the input of the channel and depends of course on the channel itself. So we have a channel here. The encoding is defined by a set of input states, rho A, and a corresponding set of probabilities. And we inject these symbol states at the input of the channel, and we collect the output state, the map applied to rho A, at the output of the channel. And the Olivo bound is defined, as you know, as you remember, I guess, as the entropy of the average output state minus the average of the entropy of each individual output state. So that's the entropy of each individual symbol state. And the single shot capacity of such a quantum channel is defined as the maximum of this Olivo bound if you maximize over all possible input and samples. And actually it has been proven, was made by Ben Hastings 3 years ago now, that such a quantity is unfortunately not, it's unfortunately not the end of the story. And if you are interested in the ultimate capacity, we need to regularize such a capacity, which means that we have to take such a limit. That's not really my point here. So my point now is to show you what is this minimum output entropy and where is the minimum output entropy conjecture that I was talking about before. So if we try to maximize this callable quantity, so we try to maximize the chi, we can do this maximization as a two-step process. We can actually first define a chi tilde, which is a quantity depending on the map and depending only depending on the average input state. I told it rho, so rho is the average input state. And so this corresponds to maximizing this quantity over all possible input and samples satisfying this constraint. So that's this thing. And then the second step is simply maximize this over rho. So why do I do this? Because then when I maximize this quantity here over all the ensembles with this constraint, you see that the first term in the oligo bound does not depend on the specific ensemble, so it's just a function of rho. And here, what I have here is a minimum of this average output entropy. And of course, it's very easy to find at least a lower bound to this quantity. A lower bound can be obtained simply by finding a state here, an input state here, which minimizes the output entropy. Obviously, if I can find phi 0, which is the input state which minimizes the output entropy, this will be a lower bound to each of these terms. So this will be a lower bound to this average here. So this will be basically a lower bound to the minimization. So an upper bound to this chi tilde quantity. So I can upper bound this quantity here if I know this state. So conclusion, we need to find a pure state, phi 0, which minimizes the output entropy. Why do I talk about the pure state? Because obviously a pure state is necessarily a state I'm looking for, because a mixed state could always be written as a mixture of pure states. So because of the concavity of entropy, the minimum output entropy is necessarily obtained with a pure input state. So now let me specify this for the case of Goshen quantum channels. This was done by Yuan and Ozawa and then by Olivo and Werner. So the only difference with what I explained before is that I consider a continuous encoding instead of a discrete encoding. So I have a probability density here, and also I need to have an additional energy constraint. So again, I have here an ensemble of states, rho alpha. I send them through the channel and I get output state. So remember, I need to maximize this capacity here. So the point is that the first term here is the maximum of the output entropy, and here I can use a very well-known property of Goshen states. This is actually a property which also exists for classical probability distributions. It is well known that if I fix the covariance matrix, or more precisely if I fix the energy, then the state which maximizes the entropy is a Goshen state with the same covariance matrix. So in other words, maximizing the first term in the Olivo quantity is very, very easy to do. It's just obtained with the terminal state. So this I can do easily. And for the second term here, I replace it with the minimum output entropy state, of course, then I only get an upper bound. All this to say that I can easily get an upper bound to the capacity if I know this minimum output entropy state. So in this particular situation, there has been a very old conjecture which is called the Goshen minimum output entropy conjecture, namely that the state that we need to inject here at the input of the channel, which results to the lowest, the state here with the lowest entropy, happens to be a vacuum state. In other words, it has been conjectured for a long time that if I inject the vacuum state here, that's how I minimize the output entropy of the channel. Let me first show you that if this is indeed true, then the rest becomes basically trivial. So if I want to compute the single shot capacity of this channel, so as I just told you, I know that an upper bound is the entropy of a thermal state input minus the output entropy when I inject the vacuum. This is only an upper bound, But the key thing is that there exists a particular encoding which is based on coherent states. I will not explain the details, but there is a simple encoding which achieves this upper bound. So this means that if the conjecture holds, then we know the single shot capacity of this channel. It corresponds to this well-known expression. This is basically the entropy of a thermal state with this number of photons minus the entropy of a thermal state with n photons. So here you recognize the two terms in the Olivo formula. So this is already a very old formula. The point is that this is indeed the capacity, the single shot capacity of such a Goshen phase-insensitive channel, provided that the Goshen minimum output entropy conjecture holds. Let me also add that the same conjecture has been made for the joint channel. So exactly, I mean, at the moment I was talking about one single channel. I was asking what's the state which minimizes the output entropy. I was saying that this state is the vacuum state. Actually, we can ask the same for a set of parallel Gaussian channels, and the same conjecture has been made. It is actually a product of vacuum states. And let me simply stress the fact that all papers on this subject always make this assumption today. So this has been very widely admitted, but it has never really been proven. There is one single exception to this, which is the case of a pure lossy channel. So, you know, this green line that I was showing in the previous figure, because in that particular case, things become very simple. In that particular case, the environment is in a vacuum state. It's just, that's why it's called a pure lossy channel. And then, of course, if I inject a vacuum state here at the input, this is also a vacuum state, therefore I output another vacuum state, which has entropy 0, and of course there is no entropy below 0. So I obviously have found the minimum output entropy state, it is the vacuum state. Okay, so for this very simple situation, the situation where I have just a single beam splitter with an environment in the vacuum state, then the conjecture is true, and we know the capacity, and this was done like 8 years ago. But beyond this simple case, if we consider any other Gaussian phase-insensitive channel, actually there is no known solution to this problem. So how have we attacked this problem? We started by using the decomposition of any phase-insensitive channel into a pure lossy channel followed by an ideal amplifier. It can be shown that this concatenation of a beam splitter followed by an ideal amplifier is a good way to generate all possible Gaussian phase-insensitive channels. So basically the transmittance tau of the overall channel is just a product of the transmittance of the beam splitter times the gain of the amplifier. And of course, if this product is itself below 1, then we are describing a lossy fiber with added thermal noise. If it's equal to 1, we describe a classical Gaussian additive noise channel. And if the product is larger than 1, then we describe a non-ideal noisy amplifier. So an amplifier where you have more noise here than strictly necessary due to quantum mechanics. So you have more than quantum limited noise. So first of all, we have shown that this conjecture, the conjecture that I was explaining, can be reduced to a specific conjecture centered on the amplifier. Okay, so let me repeat. The conjecture, if you have a Gaussian channel like this one, is that the input state sigma, which minimizes the output entropy, so the entropy of n of sigma, is the vacuum state. Right? So the minimum of this is given by the channel applied to the vacuum state. So we can focus on the second conjecture, let's call it conjecture 2, which is the same conjecture but related with the amplifier only. So this conjecture is about the fact that if we minimize the output entropy of the amplifier, then we say that the input of the amplifier should be equal to the vacuum state. Okay, so the minimum, I call this state here, I call it sigma tilde. So the minimum over all sigma tilde of the entropy of the output state is given by the entropy of the amplification of the vacuum state. So how does this reduction work? It's actually very simple. So we are injecting a state sigma. After the loss, it becomes sigma tilde, and after the amplifier, m of sigma is just the amplifier applied to sigma tilde. So we assume that the conjecture number 2, the one for the amplifier, holds. So we know that the entropy here is lower bounded by the entropy when it's applied to the vacuum. And we realize that this is saturated if we have state here. But I've already explained that in order to have the vacuum state here, it's enough to inject the vacuum state here. So actually, if I can prove that the conjecture is true for the amplifier alone, then I can induce that it is also true for the concatenated channel. So it's actually enough to consider the conjecture for the amplifier alone. So in other words, I've proven here that it is sufficient to prove the reduced conjecture. It's of course also necessary because an amplifier is just one particular Goshen channel. So it's actually necessary and sufficient to prove the conjecture for the amplifier. And the nice thing about talking about the amplifier is that I can now use the Stein-Spring dilation theorem, and I can see the amplifier not as a map, but as a unitary operation acting on two modes. So I can look at the amplifier as actually a two-mode squeezer, because this is a two-mode squeezer. And instead of talking about the entropy of the output state of my amplifier, I can talk about the entanglement between the two output modes of my two-mode squeezer. It's well known that since I'm only talking about pure state here, the only measure of entanglement is the von Neumann entropy of the reduced state. Okay, so minimizing the entropy of this is just like minimizing the entanglement. So basically that's what I'm talking about. I have one mode in an arbitrary state. The second mode is in the vacuum state. I'm processing this through a two-mode squeezer, and I'm looking at the output entanglement. So therefore we have actually our second conjecture, conjecture 2, can be restated as a conjecture of the entanglement. We can talk about a Gaussian minimum entanglement conjecture. So what we are actually doing here is that we are comparing the two-mode state that we get here if we inject an arbitrary input state, phi. We can compare this state to the state that we would obtain if you would inject a vacuum state here. So if we inject a vacuum state in the two-mode squeezer, what we get is the well-known two-mode vacuum squeeze state, so the EPR state. So I call it V. So the conjecture 2 bit is that if we try to minimize the output entanglement here, over all possible input states here, the minimum will be achieved if I inject a vacuum state here. Okay, so now I have a conjecture about the entanglement which is generated in the two-mode squeezer. So I'm getting away from the problem of the channel. I'm talking now about the two-mode squeezer. So how can we prove such a conjecture? I haven't said it until now, but actually it is rather easy to prove it for Gaussian states only. So if I'm restricting myself to injecting Gaussian state here, then as I've told you, then I will have to deal with the Gaussian formalism, because this is a Gaussian state, that's a Gaussian state. The two-mode squeezer itself is a Gaussian transformation. Then everything is very simple to compute, and I can indeed prove that the input state which minimizes the output entropy happens to be a Gaussian state. Unfortunately, that's not the end of the game, because I have no reason to restrict myself to Gaussian states. I actually don't know about what would happen if I was injecting a non-Gaussian state here at the input of the two-mode squeezer. Of course, what I could do is expand an arbitrary input state here in some basis, for instance, in a Fock basis. And what I will show you now is that we can at least prove that this conjecture holds if we focus on a particular Fock state. So we can't prove it at the moment for a superposition of Fock state, but we can at least prove it for each Fock state. So the trick is the following. Consider a two-mode squeezer, and consider the situation where I inject a particular Fock state here at the input. So at the output of the two-mode squeezer, I will get some state, which is easy to write here. So here we recognize the Schmidt coefficients of this bipartite pure state. The Schmidt coefficients are just a function of R. R is the squeezing parameter of the two-mode squeezer. And the goal is to prove that if I increase the number of photons here, so if I increase K, my entanglement can only increase here at the output of the squeezer, of the two-mode squeezer. And this actually can be proven rather easily. I just use a Pascal identity, so I just use some recurrence for the binomial coefficient. I didn't mention that you have a binomial coefficient here, so I use this well-known Pascal identity, and this allows me to write this probability, which is in the Schmidt coefficient, to write it for K plus 1 input photons as a function of the same with K photons, and another one with K plus 1 photons, but shifted by 1 unit. Anyway, the point is that this is just a convex mixture, so this probability distribution can be written as a convex mixture of two probability distributions, because lambda square is between 0 and 1, so this can be simply seen as a convex mixture. Since the entropy is a concave function, I conclude that the entropy of this is larger or equal than the average of the entropy of this plus the entropy of this. And here actually, this is the same entropy that I have here. So if I put this term on this side, I conclude very simply that the entropy when I inject k plus 1 photon can only be larger than the entropy when I inject k photon. This is an analytical truth. This is true for all values of k. This is also true for any value of the squeezing parameter. So let me show you here how it looks like. So here I'm plotting the the entanglement which I collect between the two output modes here as a function of the squeezing parameter. And I plot this for different values of k. So when k is equal to 0, that's a well-known curve, that's just the entanglement of the two-mode vacuum squeeze state as a function of the squeezing parameters. Because the stronger you squeeze, the higher your entanglement. But here, the other curves here correspond to the same situation, but when I inject more than, when I inject 1 photon or 2 photons or 3 photons here at the end. What I've shown you here is that basically the entanglement increases as a function of k. You may of course also say that this was obvious from this numerical simulation, that there was no need for an analytical proof. On the other hand, who knows what will happen when k is equal to 10 to the 10. It is of course necessary to be sure that the entanglement will monotonically increase with k. Also, we need to prove it for all values of the squeezing parameter. So now, the main point is that we have realized that this behavior that you see here is actually just the tip of the iceberg of majorization theory. What is really playing a role here is actually majorization theory, that I will explain in a minute. So let me quickly summarize majorization theory. I don't know if you know about majorization theory or not, but let me summarize it in simple words, in simple terms. So majorization theory is a way of, it's actually a partial order relation between the probability distributions. It is a way of expressing the fact that one probability distribution is more random than another one. And more precisely, we say that the distribution P majorizes the distribution Q if it is possible to convert P into Q by applying a random permutation. So you see here an example. I basically shuffle this probability distribution, so I get another one which is more flat. And this one has been obtained by applying a random permutation to the original one. So mathematically speaking, this means that the distribution Q is obtained by applying a doubly stochastic matrix to the input distribution P. In the criterion, the majorization criterion can also be written as a function of the probability distribution itself. If I first sort the elements by decreasing order for P and for Q, then I can express that the cumulative probabilities of P are larger than those of Q. It's a bit more technical, but basically it means that P is more peaked than Q. And it can also be shown that still another condition for majorization is the fact that if I take any concave function, h of x, then if I apply this concave function to the first probability, it should be lower than if I apply to the second one. For instance, if, as an example of a concave function, I take minus x log x, the entropy, then I conclude that if P majorizes Q, then the entropy of P is lower than the entropy of Q. Obviously, this simply means that the entropy can only increase in such a transformation. My main point here is that, of course, if P majorizes Q, then the entropy can only increase. That's rather obvious, but the opposite isn't necessary. But, the fact that P majorizes Q is a much stronger condition than the condition that the entropy increases. Because to go the other way around, we should prove this for every concave function, not for the entropy function. So the nice thing is that this notion of majorization can also be applied in the quantum situation. In the case where I'm comparing two pure states, if I'm comparing these two bimodal pure states, then we recognize two probability distributions which are hidden in the Schmidt coefficient here, P and Q. And we will say that the state psi majorizes the state phi if the distribution P majorizes the distribution Q. And it can actually be shown that, again, if such a majorization condition holds, then there is a possible interconversion between the two states. So here it works the other way around. So it can be proven that if psi majorizes phi, then there is a deterministic LOCC operation which will go from phi to psi. And I mean, I'm skipping all the details, but as a consequence, it also shows that the entanglement of this is low or equal to the entanglement of this, which means now that the entanglement at this time can only decrease along an LOCC, which is again something we know very well. So we know that along an LOCC the entanglement can only decrease, but it is a stronger condition to say that these coefficients should majorize these coefficients. So that's basically all I wanted to say about majorization. So let me come back to my problem. So here, remember I'm talking about the two-mode squeezer, which is actually just a Bogoliubov transformation between the two modes. I'm injecting here an arbitrary state and a vacuum state, and I'm looking at the joint output state here, and I'm comparing the actual output state, the one that I get if I inject phi, with the two-mode squeeze vacuum state, the one when I inject the vacuum. And now the new conjecture that we have made, which is even stronger than the Goshen entropy conjecture before, is that the two-mode vacuum squeeze state here majorizes the two-mode state phi for any input state. So in other words, the two-mode vacuum squeeze state that I get here if I inject the vacuum here majorizes every other possible two-mode state that I would get by injecting anything I want here. So this is actually a very strong condition. This would mean that phi can be converted into the two-mode vacuum squeeze state by applying an LOCC. And this would in particular imply what I need, namely that the entanglement of the two-mode vacuum squeeze state is indeed a lower bound to the output entanglement. So this would prove the conjecture. This is actually a stronger conjecture than the minimum entropy conjecture. But the hope, of course, is that it may be easier to prove, to tackle the problem in this way, because manipulating the entropy is typically a difficult thing to do. And here we hope to circumvent this problem and attacking the majorization problem itself. And actually it so happens that we can find some partial results. So for instance, that's the curve that I showed you before. Indeed, we can really show that there is a majorization relation between all these distributions. So in other words, if I look at the two-mode state with, for instance, 2 photons at the input, and I compare it to the two-mode output state when I have 1 photon at the input, indeed I can show that there is an explicit LOCC going from one to the other, so I can really show that this is the reason why the entanglement here was larger than the entanglement there. So this majorization, this Goshen conjecture actually originates from a stronger relation which is related to this majorization. So I will also skip the explicit LOCC. I mean, on the way when we were studying majorization, we got to realize that majorization plays a key role really in the two-mode squeezer. I mean, here, before what I showed you was that the majorization as a function of k for a given r. So I was fixing the squeezing parameter, and I was comparing several values of k, and I was showing you that there is a chain of majorization relations. There is actually something very similar if now you fix k and you look at different values of the squeezing. So here you can again show that there is really a majorization relation on each of these curves if you compare several values of r. So in other words, let's for instance consider the simplest case, k is equal to 0. Here I'm simply saying that the fact that when I increase the squeezing parameter I get more and more entanglement at the output is actually a consequence of a stronger result, which is that each of these states is majorized by these states. And actually we have shown that the same majorization relation holds for each of these curves. So there really seems to be something very, very basic here in majorization in a two-mode squeezer. And one of the consequences of this would be the Goshen conjecture, but there is more than this conjecture. So before concluding, let me show you what happens if we now apply some superposition of Fock state, because up to now I was considering an input state which was just a particular Fock state. But what happens if I I inject an arbitrary superposition of Fock states. So for instance, what happens if I inject a superposition of 0 plus 1? I will have a curve like this one here, which is in between the curve for vacuum and for one photon. But even more, that this is just comparing the entanglement, comparing the entropy. I can numerically prove that each of these states is indeed majorized by the corresponding state when I inject the vacuum. So in that sense, I can really prove that the vacuum is really what minimizes the disorder, in the sense that each of these states is really majorized by the two most vacuum state. Unfortunately, things are not that simple. An example of the problem can be seen here. If I now consider, for instance, a superposition of 1 and 2 photons at the input. So this corresponds to this blue curve. So here, in this region, the entanglement is a bit larger, and you may believe that this is a sign that this state is majorized by the state with 1 photon. But actually, it's not true. If you go to larger squeezing, you see that there is a crossover, there is a crossing here, and you see that the blue curve is here. So actually, we can also check it numerically, that it's already visible here, that this state isn't majorized by the single photon state. This does not contradict the conjecture, because we can prove numerically again that this is indeed always majorized by the vacuum state. But it's not, the structure of majorization isn't unfortunately very simple. So before concluding, let me just mention that we believe that this, what we have been seeing here, is actually a counterpart, or maybe connected to some counterpart of a well-known classical information theoretical inequality. In classical information theory, there is something known as the entropic power inequalities, and it is probable that there is something similar here in a beam splitter. Remember, I started by saying that when you play with entropies in a beam splitter, things become complicated, even though if you look at the beam splitter here, you see that it is really nothing else but a rotation, or I said a rotation between A and B. So this is a very simple object, but if you look at this object in state space, things become very complicated. So what we really need is a lower bound to the output entropy. And actually, this is again not proven yet, but it may be that there is an inequality like this which connects the so-called entropic photon number. So the entropic photon number of a state would be defined as the number of photons of a thermal state having the same entropy as the actual state. So each state, you can compute its entropy, and you have a thermal state with the same entropy, and you can look at the number of photons contained in this thermal state. That would be called the entropic photon number, and it is probable that the entropic photon number of the output state is lower bounded by this linear superposition. So this may be another way of attacking the conjecture. So let me insist on the fact that we believe this is not just an abstract mathematical problem. You may think that this is just about quantum information theory, about how do entropy, what's the entropy with a beam splitter or thing like that. So, but even if you don't care about quantum bosonic channel, let me insist on the fact that all this is at the end about the Bogoliubov transformation. Now I was talking about two-mode squeezer, but this Bogoliubov transformation is of course really ubiquitous in physics. We have it in quantum optics, we have it in superconductivity, Hawking radiation for black hole, the Henry effect. So in many situations we know that this Bogoliubov transformation is central. So it is possible that this Goshen conjecture may have a deeper physical implication there. So really the question that we are, in case you haven't understood it, the question that we are really trying to solve here is really to prove that nothing is less random than the vacuum state in such a Bogoliubov transformation. So, take home message, we have shown that we have proven a new approach to solve this conjecture. So it works by reducing the conjecture to the case of an ideal amplifier channel. So remember, if we can prove the conjecture for one amplifier channel, that's enough to prove it for every Goshen channel. And then we have linked this to a conjecture about the output entanglement of a two-mode squeezer. And then finally we have linked this with majorization theory. So it's interesting to realize that the proof that we have at the moment is a partial proof, because it only works for Fock state at the input. On the other hand, we know that the Fock states are the only pure states which are phase invariant. So if there was any way of proving that the input state which minimizes the output entropy should be phase invariant, then the proof would be finished. Basically, we would have the proof. The point is that we have no good argument to convince ourselves that there can't be any symmetry breaking. So we simply cannot rule out the possibility that a state which is not phase insensitive at the input would give rise to a lower entanglement or lower entropy at the output of the channel. On the other hand, as I have already shown you, the numerical analysis strongly suggests that this conjecture is true. Even the stronger conjecture, so the majorization conjecture, really seems to be true from our numerical analysis. Okay, thank you.
Questions? Thank you, Nikolai.